Hey everybody, welcome back to another round of astronomy. And yeah, let's get going. So let's go ahead. Let's get into telescopes. Here I have just a little figure. Remember, I told you that there are different types of light, and unfortunately, there isn't a jack of all trades for telescopes. These four telescopes comprise the great NASA observatories. It was part of a program to launch several telescopes that would cover different types of light in order to give us a well-rounded perception of what's going on in space. So here I have for you is, well, for example, we have the CGRO. That's an acronym for the Compton Gamma Ray Observatory. So that telescope is optimized to collect gamma rays from outer space. If we go slightly down the list to X-rays, we have the Chandra X-ray Observatory. And just for completeness, there is a European equivalent called the XMM Newton. Both of those are X-ray telescopes. Then, of course, you're probably familiar already with the HST, the Hubble Space Telescope. And then lastly, invisible light. And then lastly, what we have down here is the Spitzer Infrared Telescope Facility. Okay? Now, all four of these were space-based, and they together help give a nice picture of what's going on. Just like that picture that I showed you where you see both the visible light, the pigment and the paint, but then you can look at infrared and see the charcoal underneath, or you could look at X-ray to see the lead places, the places where Raphael did some whiteout. Here we have that full complement of telescopes to just get a better picture of what's going on in clouds of dust, space, etc. Pretty cool, huh? So that's some telescopes. The thing I should ask you, so pause the video for a minute, and we really should talk about the important physical properties of a telescope. What are the things that I should look at when I'm talking about a telescope? So pause the video for a second, but give me an idea. Which eyeball collects more light? You got it? Yeah, good. And we look at this and we say, well, Greg, the eye that collects the more light is the one that has the larger pupil. And so if it's bright outside, your pupil contracts to not let as much light come in. And when it's rather dark, it dilates to let more of that light in because there's not as much of it outside. So one of the important physical properties of a telescope is what we call the aperture. Or if you prefer, the light collecting area. So we should ask ourselves, how do you calculate that? So next question, go for it. Which formula gives you the area of a circle? Go ahead, try it out real fast. No, don't look it up. Pause the video, see if you can come up with it. You got it? Yeah, good. Okay, well, for those of you that have it, I applaud you. Great job. For those of you that weren't quite sure, you're like, maybe this, I think it might be that. Let's walk through it real fast. So the first thing that we should do is we should recognize that area requires the radius to be squared. Okay? Remember, the units of area would be something like meters squared. Okay? So we can come over and look and say, well, which of these answers will not give us the proper units, meters squared? We go, okay, well, let's see here. Oh, R, meters divided by pi. This doesn't give me meters squared. Oh, okay, meters squared. Oh, this one doesn't give me meters squared. And okay, so we can eliminate a couple of these options just by looking at the units. Incidentally, if you're interested, 2 pi r might look familiar to you. That's the circumference of the circle, or the perimeter. This is circumference. Okay, so B and E are out. Well, how else can we get this? Now, if you don't remember the exact equation, that's okay. Okay, I can always help work you through this. We've got three options. Okay, so the next trick I'll show you is, let's think of a minute, not of the circle, but let's think of surrounding the circle with a square. Okay, and if I surround that circle with a square, we know that the side length of the square is 2r, twice the radius. And so the full area of the square should be 4r squared. Good so far? Okay. Now remember that we built the square so that the circle just fit into it. Okay? Which means the area of a circle should be around 4r squared. And I should say smaller than 4r squared. Right? Because there's a little extra space. If I go back, there's just a little extra space. Okay? So now we go through. We say, well, 2 pi r squared. That 2 pi is closer to 6. It's greater than 4. So this one can't be it. Okay? We already argued the area has to be less than 4. Okay? Now this one's less than 4. This one's about 0.33 r squared. Too small, right? Oh, I feel like Goldilocks here, right? This one's too big, this one's too small, but this one is just right. So there we go. The area of a circle is given by pi r squared. Okay? Which means if we want to determine how much light a telescope can collect, it is proportional to the area of the telescope. Well, yeah, let's go ahead. This is why we want to build bigger telescopes. So I thought I would at least show you this infographic again, shamelessly stolen from Wikipedia, which gives you a sense of comparison of some of the telescopes and how large they actually are. So you have things like the Hubble Space Telescope, which is a 6-foot mirror, compared to the James Webb Telescope, which is closer to 20. Okay? Of course, your Meade ETXs are just a mere 90 millimeters in diameter, about 3.5 inches. The extremely large telescope is currently under construction. In fact, this was an image taken about 2 years ago where they were pouring the concrete foundation. And I believe this is being built in, oh yes, it's in Chile. The reason for Chile, or for Hawaii for that matter, has to deal with how far above the clouds you can get. So in Hawaii, we build our telescopes on Mauna Kea. It is tall enough that you can get above the atmosphere and not have to worry about as much water vapor, which absorbs light. You don't have to worry about clouds, which prevents light from being transmitted down to the surface. You can get above a lot of the atmosphere and weather patterns, and that means more nights with better weather. The same thing happens down in Chile in the Andes mountain range, is that they're low enough that you can do the construction and the weather is fairly moderate, but they're high enough above sea level to get above these weather patterns in these clouds. So the other thing that I would like to share with you is the magnification of a telescope. We have the light collecting area that determines how dim of an object you can see. The other thing that we should look at is how large can I magnify the object? And you've already seen this in lab, is that if you switch out the eyepiece of the telescope, you get a different magnification. Okay? So let's go ahead and quantify that. So the first thing that I have to define for you is what is meant by focal distance. That is the distance that light has to travel inside the telescope before it is focused at a single point. Okay? For our telescopes, the light travels a longer distance in order to become focused. The telescopes you use in lab the light travels about 1.5 meters before it is actually focused on a single location. And it does that using mirrors. It reflects back and forth several times. So, yeah, okay. So I'll give you the equation for magnification now. Okay. So the magnification that you can achieve with a telescope is given by the focal length of the telescope divided by the focal length of the eyepiece. Okay. So as you swap eyepieces, generally you start off with about a 25 millimeter eyepiece. And go ahead, when you're in lab, excuse me, go ahead, open up the box and you'll look on the side of the eyepiece. There'll be a number printed, 25 millimeters. The other eyepiece, that's the long one, right? That's the big eyepiece. The smaller eyepiece, I think, is something like 9 millimeters, or maybe, yeah, let's say 9 meters, and that's the shorter one. Okay? The reason it's shorter is because light doesn't have to travel as far in order to become focused. Okay? So this is one of the advantages that telescopes have over something like binoculars, is although you can't change the focal length of the telescope, you can swap out eyepieces to change the focal length of the eyepiece. And I should learn how to spell. This is length. Okay. Okay. And that's basically it. As the focal length of your eyepiece goes down, you get a higher magnification. As the focal length of your eyepiece goes up, you get a lower magnification. If you have trouble finding an object in the night sky looking through your telescope, the first thing I'll tell you to do is drop in a larger focal length eyepiece. That will demagnify what you're seeing in the telescope and give you a larger field of view. Makes it a little bit easier to actually find objects in the sky. Pretty cool. Now I've just short scripted it. I say magnification is the focal length of the telescope over the focal length of the eyepiece. Well, let's go at it real fast. Give me an idea. What's the focal length of the Meade ETX? So this is the one that we use in lab. I give you the focal length is 1.25 meters, and we'll say a 25 millimeter eyepiece. Go ahead, pause the video. Tell me, what's the magnification with this combination? You got it? Yeah, good. Well, at this point, we just drop in the two numbers. We have the focal length of the telescope. We have the focal length of the eyepiece. We can just divide those two numbers. And you should get something around a 50x magnification. And I encourage you, keep that in your head, just because it's a nice round number. If I use the standard eyepiece in my telescope, it's about a 50x magnification. Okay. Well, I think that is by far more than we probably needed, but I just wanted to give you an idea about some of those telescopes and the main physical features, the light collecting area of the telescope, and the magnification. So hey, I'll leave it there. Make sure to write down questions, bring them to class. We'll discuss a little bit more in person on Monday. I thank you for your attention. Keep up the good work. I'll see you next time.